All right, welcome back for another video. This time we're going to talk about arc length of parametric curves. Before we do that, first we need to sort of have a formula for this thing. It's actually a pretty neat result deriving this from the arc length integral for our rectangular curve, which was the integral from one x value to another of the square root of 1 plus dy dx, or the derivative squared dx. So let's see if we can do a little bit of manipulation and figure out how we can translate this arc length formula to one where we're going to have a derivative of x with respect to y, but also a derivative of a derivative of x with respect to time, but also a derivative of y with respect to time. So let's start out by, I'm going to rewrite two things at once. I'm going to take this integral and I'm going to make this one a special kind of one. I'm going to make this one a giant one of dx dt squared over dx dt squared. So maybe I should rewrite my integral to be a little bit larger here. Plus, I'm going to rewrite dy dx as dy dt over dx dt, and just put it into that parametric form. And of course, that is squared dx. The cool thing about this is I can actually kind of dig in and use the power of the eraser. I'm going to sort of make this two separate pieces and say, well, that's really the same thing as dy dt squared over dx dt squared. And from there, I can use my common denominator to add these fractions together. So I get the integral of the square root of dx dt squared plus dy dt squared all over dx dt squared dx. Now I can dig in a little bit further. I'm actually going to rewrite this with the eraser once more. And instead of having the square root of the entire quantity, I'm going to take the square root of the numerator and the square root of the denominator. Well, that means that really my denominator can be rewritten as, well, the numerator stays the same, dx dt squared plus dy dt squared over dx dt dx. Okay, well, if I have dx out here, and I really have 1 over dx dt times dx, that's the same thing as saying dx dt, or I'm sorry, dx divided by dx dt. That's the same thing as writing dx times, multiplied by the reciprocal to divide, dt dx. Giant one, see you later. So this original multiplication can be rewritten as just dt, which means my integral is really the square root of dx dt squared plus dy dt squared dt. And there you go. I have my arc length formula. If I'm given some x equals y equals parametric curve combo here, I can find dx dt and dy dt and use this formula from A to B. Now, in terms of time, to find the arc length of a curve. This is really simple to do. We'll keep this on screen. We'll flip our colors and just go to another example here. Let's use x equals t squared and y equals root t plus 3. Well, let's see. dx dt is equal to 2t. dy dt is simply 1/2 t to the negative 1/2 power. And all I have to do is take these two and put them in for dx dt and for dy dt over some interval. Maybe I want the interval from, I don't know, 1 to 4, right? And again, this is a time interval. So my final arc length integral would be the integral from 1 to 4 of the square root of 2t squared plus 1 half t to the negative 1 half squared dt. You could simplify that if you wanted to. You could make that the integral from 1 to 4. Oh, hold on a second. The integral from 1 to 4 of the square root of 4t squared plus, I could rewrite that as, what do you want here? How about 1 over 4t dt? I'm not going to be able to go much further than that by hand, but now you have an integral that you could probably pick out of a multiple choice lineup or put into your calculator from time equals 1 to time equals 4 to find the arc length of the parametric curve between those two time values.